thermal expansion, all right? The thermal expansion, I told you, the change in the length due to some temperature, right? So most solids materials expand upon heating and contract when cooled, right? So when you increase the temperature, length will also increase. When you decrease the temperature, length will also decrease, right? Common phenomena. And contract when cooled, right? So the word contract means reducing, okay? The change in length with temperature for solid material may be expressed as follows. So this is a formula to calculate the change of the length of a material with the change in the temperature, right? So LF minus L naught over LO equal to alpha into TF minus TO, right? So this LF is the final length, right? Final length means you heat it, and after heating it, that will reach some temperature now. So say for example, at T1 degree Celsius, this is L1, okay? At T2 degree Celsius, this is L2. Okay. So due to the change in the temperature T2 minus T1, due to you provide like some extra heat, this much increase has happened. Okay. So when you put these terms into this equation, LF is the final length. So that is L2, right? L2 minus LO is the initial, right? Initial length. So initial length is L1, right? L2 minus L1 upon LO, that is the initial length, L1 equal alpha. Alpha, I told you, it's given in the table, that is different for different materials. So thermal expansion coefficient. So that alpha into TF, that is change in the, not change, that's the final temperature. F means final, right? So final temperature here is T2 minus TO. TO means initial temperature. Initial temperature here is T1. Right? So L2 minus L1 is equal to L2 minus L1 upon L1 is equal to alpha into T2 minus T1. So if you want to write this formula into these terms, right? So this term I just drawn to indicate you how is it actually happening, is equal to like this. So in other words, we can say delta L upon L naught, right? So this is the delta L, y change in the length, L2 minus L1. So that is only this much. So this can be written in other format also. So when you see LF minus L naught, that is L2 minus L1. So this is L2, this is L1, L2 minus L1 is this length only, right? That is actually the increased length. So I can put it as delta L. Why? This is the increased length divided by L naught, right? L naught is the initial length. So that's why this L naught is will be equal to alpha into, right? Alpha is the thermal expansion coefficient into TF minus TO. So TF is the final temperature, TO is the initial temperature. So final temperature minus initial temperature is the change in the temperature, right? That is delta T, right? So this equation and these equations are similar equations, right? So this way, or this way, or this way, these all are same. Delta L upon L is equal to alpha into delta T. You can say like that. Or else final length minus initial length upon initial length will be equal to alpha into final temperature minus initial temperature, right? These two are same formulas, right? This and this. Only thing is they are written in different format, where L naught and LF represent respectively initial and final lengths, right? So L naught I told you initial length, and LF is the final length with the temperature change from TO to TF. Again, T naught is initial temperature and TF is final temperature. The parameter alpha L is called the linear coefficient of thermal expansion, right? So alpha, I told you, that is linear coefficient of thermal expansion. So there's an L is there, right? So this L is for linear coefficient. If it is V, that would be volumetric coefficient, right? If it is A, that is area coefficient, right? So when you see alpha L, that is linear coefficient. Okay, linear coefficient. So that will indicate the change in the length, initial length and final length. Okay, and if you have alpha A, that is area, right? Area coefficient. So that will give you an idea of the initial area, and when you heat it, the final area. Okay, and then we have alpha V also, right? So that is actually volumetric coefficient. So that will show you, you know, a change in the volume. So if this is the initial volume, the final volume. Okay, these figures are not that good, but you can just imagine, no? So volume itself increasing means this way length should increase, this way width should increase, and this way height should also increase. It's a material property that is indicative of the extent to which a material expands upon heating and has units of reciprocal temperature C minus 1, right? Delta, sorry, not delta C, degree Celsius minus 1 is the unit of alpha. So how much extent a material can expand when you provide some heat. Okay, so this will be different from material to material. Say for example, you are providing 10-degree increase in heat for both aluminium, copper and iron. Okay, so aluminium has a higher thermal expansion coefficient, so that will expand very much. Copper must have next to that, that will expand this much. But iron very low, so that may expand this much. But for all three materials, you have provided 10 degrees Celsius, right? Equal amount of heat. You provided an equal amount of heat, but they show different lengths. So this is the property of that material, which is denoted by the alpha thermal expansion coefficient or linear coefficient of thermal expansion. Of course, heating or cooling affects all the dimensions of a body with a resultant change in volume. Volume changes with temperature may be computed from delta V upon V naught is equal to alpha V into delta T. So in the similar way as like linear, so that was delta L upon L naught is equal to alpha L into delta T. That is linear expansion coefficient, linear change in the length. Here, when it comes to volume, you have to just replace this all L with V. So delta V upon V naught will be equal to alpha into V into delta T. If it is like area coefficient, then delta A upon A naught will be equal to alpha A into delta T. That A would be indicating the area, right? So you can compute the value of either delta L or delta A or delta V by putting in this formula, right? Where delta V and V naught are the volume change and the original volume. So delta V is the volume change, V naught is the original volume, right? Respectively, and alpha V symbolizes the volume coefficient of thermal expansions, right? So alpha V shows the volume coefficient of thermal expansion. What you see here is alpha L, that is linear coefficient of thermal expansion, right? In many materials, the value of alpha V is anisotropic, that is, it depends on the crystallographic direction along which is measured. For materials in which the thermal expansion is isotropic, alpha V is approximately 3 alpha L, right? So for materials, thermal expansion is isotropic, right? So when there's a continuous or uniform change, this alpha V would be almost equal to 3 into alpha L. Okay, alpha V will be almost equal to 3 into alpha L. So this and this are alpha. This is a direct proportional sign. In a similar way, alpha A is directly proportional to almost, I can write even equal, right? Not always, to alpha L. Let's see how is that. So for example, you have a length here, okay, and you heat it and you now got a new length, this one, okay. If you have an area, right, so when you heat this area, okay, when you heat it, what will happen? Along this length also length will increase. Along this length also length will increase. So this will come like this, and this will go like this. So here you see this way an alpha L is occurring. This way an alpha L is occurring, right? So here we have 2 alpha L, right? So that's why alpha A can be stated as 2 into alpha L, right? Only thing is it should be in isotropic condition. Isotropic means a kind of uniformity in increasing, right? Similar way I can explain for volume change also, right? Volume means along with this area I will have a thickness, right? I will have a thickness. Say for example, this is my initial material, right? So when you heat this, what will happen? Length will increase like this. Okay. So at the end, I will ended up in having a material like this. So here I have already an alpha 1, sorry, not alpha 1, alpha L, that is linear coefficient of thermal expansion. This way another alpha L, and this way down the z-axis also I have an alpha L, right? So if I say this is x-axis and this is y-axis and this is z-axis, so x-axis I have alpha L, y-axis alpha I have alpha L, and z-axis also I have alpha L, which means now I have 1, 2 and 3 alpha L, right? So that's why this alpha V can be written as 3 alpha L, right? So that's why it's stated that for materials in which the thermal expansion is isotropic, alpha V is approximately 3 into alpha L, right? Approximately, right? It's approximately, not exactly equal, but approximately. Atomic perspective, thermal expansion is reflected by an increase in the average distance between the atoms, right? So I told you, when you provide energy, they won't stand at a place. They will keep on running here and there and everywhere, right? So due to this, the distance would be increased, right? Distance between the atoms would be increased. So this is how the thermal expansion is happening in the um, perspective of the atomic. So say for example, in this volume, initial volume, I had 4 atoms, right? Now they are in this distance. Okay, this is the distance. When you heat, what will happen? They gain energy, but they want to move here and there. So they will agitate or vibrate. So at that time, they anyhow will move. So this electron may move here, right? This electron may move somewhere like this. This can move like this. Okay, this can move like this. Why? Because they got the energy, so they can move. So when they are moving, that's a material. So if the electrons are moving, mean they are making high space, right? So due to that, the area is increasing, right? Due to that, the area is increasing. So this is the same phenomenon as like here, but here the perspective, I mean, what I am talking is about the movement of the atoms, right? Here what I am talking is about the, I mean, mathematical way, right? So thing is similar, but the way I am explaining is different. As noted in the table, linear coefficients of thermal expansion for some of the common metals range between 5 to the 5 into 10 to the power minus 6 and 25 into 10 to the power minus 6. So if you see the table, so all the metals, the range was like this. These values are intermediate in magnitude between those for ceramic and polymers, right? So if you check them, these values, these are lying between this value and this value. So these are lowest, these are next, and these are the largest, right? So here you see the values are ranging from maximum 25, 23 to minimum around 5.1, 1.6, right? So that's what he is talking about. These values are intermediate in magnitude between those for ceramic and polymer materials. As the following materials of importance box explains, several low expansion and controlled expansion metal alloys have been developed, which are used in applications require dimensional stability with the temperature variations, right? So Yeah, here we have a table, right? Materials of importance. Invar and other low expansion alloys. We will study that one. So why actually the table is important is because usually when we heat, you know, material will expand. So if the material is expanding, which means the dimension is high, right? So for materials which needs thermal stability, right? Thermal stability, we develop some materials, right? We develop mean kind of alloys are made, right? So say for example, usually the which one we'll assume piston, right? So we'll assume piston, right? And piston ring. So you know, piston ring has to move back and forth inside the piston, right? So you just assume this is piston and piston rings, even though my drawing is not that good. Okay, so this should move up and down, right? So this region we will have a seal, and this region also we will have a seal. Okay, and fuel will be supplied by one way and go out by the other way. Now my question is, when the fuel is applied and when there's pressure generated and fire occurred and then fuel will be exhausted. You might have studied this one in the automobile foundation automobile subject. So that's a phenomenon of ignition. When this thing happened, the engine usually actually piston and piston ring at room temperature, say for example around 30, will be rising to around some thousands of temperature. I'll put like 1000. Okay, 500 fine. Okay, so initially that is at room temperature, that is 30 degrees Celsius. Now it has increased to 500 degrees Celsius, which means according to what we have studied so far, there should be a thermal expansion, right? There should be a thermal expansion. But if there's thermal expansion at high temperatures, this gap would be fine for the metal to move. But at low temperature, this gap will be very large, which we don't want, right? So there are certain incidents where we need the thermal expansion to be controlled. We cannot leave it as it is. All right. So for those particular moments and applications, there are some alloys developed. Right? So that's what this sentence is mentioned about. Materials of importance also explain several low expansion and controlled expansion metal alloys. So here the expansion is deliberately controlled, which are used in applications require dimensional stability with temperature variations, right? So with the temperature varying, what's actually happening to the dimensional stability? So dimensional stability, I told you, not changing like frequently for the change in the temperature, right? So let's see that in 1896, Charles, this guy of France, made an interesting and important discovery that earned him the 1920 Nobel Prize in Physics. Okay, he earned it. An iron nickel alloy that has a very low, near zero coefficient of thermal expansion between room temperature and approximately 230 degrees Celsius, right? So this alloy, iron nickel alloy, right? Iron is Fe, nickel is Ni. That has a very low coefficient of thermal expansion, so nearly zero. So does not have any thermal expansion between this range, room temperature and 230 degrees Celsius. So room temperature may be 30 degrees Celsius and this temperature would be 230 degrees Celsius. This material became the forerunner of a family of low expansion, also sometimes called as controlled expansion metal alloys, right? So he made it as a low expansion alloy. So this would be the first foundation for that. Its composition is 64% Fe and 36 weight nickel. So in that composition, 64% by weight is iron and 36% by weight is nickel. And it has been given the trade name of invar because the length of a specimen of this material is virtually invariable with changes in temperature, right? So up to this, I mean, in this temperature range, 30 to 230, the change in the temperature is like a kind of negligible. So in other words, we can say that is invariable. There is no variation in the temperature. So that's why the name invar is given. So first 5 letters INVAR, right? So that's why this name metal is called as invar, not metal, sorry, alloy, right? So alloy of 64% weight Fe and 36% weight Ni is called as invar because the variation of temperature is low, sometimes invariable, right? That's why the name is given. Its coefficient of thermal expansion near room temperature is 1.6 into 10 to the power minus 6 degrees Celsius minus 1, right? So when compared to aluminium, which is around 23, and gold around 13, silver around 17, this is very much less, around 10 to 12, 10 to 15 folds lesser than that of the thermal expansion of those metals, right? So this is the specialty with this invar, that is 64% Fe and 36% Ni. Heat treating and processing of invar will also affect its thermal expansion characteristics. The lowest alpha L values result for specimens quenched from elevated temperatures that are then cold work. Annealing leads to an increase in alpha L. So if they want to change that property, they will go for some heat treatment process. Other low expansion alloys have been developed. So there are some others also. One of these is called super invar, right? Because invar it has a thermal expansion of 1.6, right? 1.6 into 10 to the power minus 6. Then they have developed even better material than that, that is showing 0.72 into 10 to the power minus 6, super invar. So this is lower than the value of for invar, so almost half. However, the temperature range over which its low expansion characteristics persist is relatively narrow, right? So here the range of temperature is little bit less. Here you see from room temperature to 230 degrees Celsius, that is around for 200 degrees Celsius, right? Room temperature 30 to 230 degrees Celsius. So which is around 200 degrees Celsius. Thermal expansion coefficient is 1/6 into 10 to the power minus 6. But for super invar, yeah, that is 0.72 into 10 to the power minus 6. That is fine. But the temperature range is the problem. So it shows only at a particular temperature range, right? The temperature range is so narrow, relatively narrow. Compositionally, for super invar, some of the nickel in invar is replaced by another ferromagnetic metal, cobalt. So super invar now has 63% Fe for 32 Ni and 5% cobalt, right? So this is actually the composition of super invar. This has a low thermal expansion coefficient, but the range for that will occur is low, right? A kind of narrow. So here we have another alloy with the trade name of Povar, right? This is Povar, has been designed to have expansion characteristic close to that of borosilicate, right? Borosilicate is refractory material, as you already studied. For Pyrex glass, when joined to Pyrex and subjected to temperature variations, thermal stress and possible fracture at junction are avoided. So this is another alloy. Right? So here 54 of Fe, 29 nickel and 17 cobalt. So the components are same, 54 Fe, 29 nickel and 17 CO. Here 63 Fe, 32 nickel and 5 CO. Right? So materials are same, but the composition is different. So these low expansion alloys are employed in applications that require dimensional stability with temperature fluctuations, including the following. So they need to stay steadily when the temperature fluctuates. So that's the purpose. So when the temperature increases, dimension will also increase. When the temperature decreases, dimension will also decrease. That's a general formula. But these materials are particularly made, which one? This invar, super invar, povar. These are particularly made for tolerating the fluctuating temperature. So which means dimension is stable when the temperature is fluctuating. Compensating pendulums and balance wheels for mechanical clocks and watches, right? So pendulum, when the temperature increases, what will happen? The length of the pendulum will increase. So if the length increases, so when the temperature increases, the length will also increase, right? So when the length increases, the swaying time will also increase, right? Swaying time will also increase. When this swaying time increases, this will not show a correct time, right? This may lag in milliseconds, microseconds, and they will collaborate as a kind of seconds and then minutes, right? That's the problem with the pendulums and balance wheels, so mechanical clocks and watches, right? So these watches and mechanical clocks, they have like small inside the wheels or gear setup, something like that, right? So you might have seen in this wall clocks, if you open it, you will find something with the plastic. That's fine. In case if it is metal, then they will, expand with thermal value. I mean, increase in temperature, and they will make problem with the times. Then I have structural components in optical and laser measuring systems that require dimensional stability on the order of wavelength of light, right? So these are few materials. Bimetallic strips that are used to actuate micro switches in water heating systems. So bimetallic strip, that is the structure of two metals, right? So these are usually used in iron box. One can be aluminium, and say for example other is Fe. So if the thermal coefficient of aluminium is high, right, this will expand fast. So when you increase the temperature, aluminium would have been here, right, and maybe this iron can go only up to here, right? So what will happen? This is tied, so definitely this has to bend like this. No, not that way. This will bend this way, right? That will bend. Okay, because this and this is tied now. This can't exhibit like this, so they will bend, right? So that's the example of bimetallic strips. Then I have shadow masks on cathodic ray tubes that are used for television and display screens. Vessels and piping for the storage and piping of liquefied natural gases, right? So these are some phenomena why this temperature fluctuations is not advisable in some particular applications, right? So this is why we need this low expansion alloys. So invar, super invar, and povar. So these alloys have very low thermal expansion coefficient. So they are preferred for particularly some applications, right? Okay, ceramics. Relatively strong interatomic bonding forces are found in many ceramic materials, as reflected in comparatively low coefficients of thermal expansion. So here the interatomic bonding is strong, low coefficient of thermal expansion, right? Typically range between 0.5 to 15. So their expansion is not very low, little bit low compared to metals. So pure silica is having a thermal expansion coefficient of 0.4 into 10 to the power minus 6. So ceramic materials that are subjected to temperature changes must have coefficient of thermal expansion that are relatively low and isotropic. Then we have polymers, right? Polymeric materials experience very large thermal expansion upon heating. So in the table, if you see, when you come, that's the table. When you compare, these have very large thermal expansion coefficient than other two. Experience very large thermal expansion coefficient upon heating and indicated in the range of around 50 to 400, right? While this is the case of metal around 5 to 20, now it's like 10 folds, 50 to 400. The highest alpha values are found in linear and branched polymers because of the secondary intermolecular bonds are weak, right? So when we are talking about these polymers, I told you, if the structure is to be strengthened, then interconnection chains must be there and aromatic links should be there, right? With increased cross-linking, the magnitude of expansion of coefficient diminishes. Why? There are too many bonds. Say for example, you have only this one. This is a polymer. Okay. You have another polymer also, right? Assume that it is bonded like this and like this, right? So this polymer will have less tendency to expand. Why? There are too many too many branches or links, cross links are there, which need to be expanded. But here that's not the case. If you provide heat, all the heat will be supplied to these single bonds and that will expand, right? So that's why it's mentioned high alpha L values are found in the linear, right? Linear and branch polymers, right? Linear and branch polymers. With increase of cross-linking, right? With increase of cross-linking, the magnitude of the expansion coefficient diminishes, right? Diminishes means reduce. So when the this chains bonds, when they increase, the thermal expansion will decrease, right? Lowest coefficients are found in the thermostatic network polymers such as phenolic formaldehyde, in which the bonding is almost entirely covalent. So phenolic formaldehyde, there's a phenol, right? So which means aromatic chain is there, right? So here the thermal expansion value is so